Hi, everyone. I'm Till. I work as an engineering lead at Bavarica, and I'm a longtime Flink contributor.
Hi there, my name is Addison Higham. I'm the chief architect here at Stream Native, and I've worked both on Flink and in the Pulsar communities.
So today we want to talk about stream processing advanced with Apache Flink and Apache Pulsar. So let's start with why stream processing is important. We believe that stream processing is very important because it allows you to process your data faster, getting your results faster, which allows you to do faster business decisions, which gives you a competitive edge over your competitors, and at the end of the day, allows you to make more revenue. Moreover, we believe that stream processing is actually the next evolutionary step from batch processing. With batch processing, you were able to process the data you have collected over some time. With stream processing nowadays, it's actually possible to do the same as well as processing live data. And what you can also do, you can combine both. Start with processing your historical data and then switching to the real-time realm once you reach the latest data. And last but not least, we believe that stream processing is actually a very powerful paradigm because it allows you not only to do analytical tasks, but also to build event-driven applications. From a engine's perspective, whether you increment some counters in order to calculate an aggregation when an event arises, or whether you trigger some business logic is actually not that different. Furthermore, you can actually combine both things. You can create applications which benefit from real-time analytics, like for example, doing fraud detection on real-time learned machine learning models. So in order to get a feeling for what kind of use cases we are talking about here, I tried to write down some of the data streaming applications we've seen in the past and try to, I tried to group them according to how much latency they allow or what kind of, how hard the latency requirements are. On the very left, we see the traditional data warehousing tasks. And on the right, it's the distributed OLTP applications. So going from left to right, have as I said, ETL jobs, which don't have very high latency requirements. So you usually process some old data. When going a bit more to the right and doing like real-time analytics or continuous monitoring of, for example, your risk positions in your portfolio, or even try to do real-time behavior modeling in order for e-commerce websites to do like the proper recommendation to their customers, you actually have some harder latency requirements. And it even gets harder when doing like real-time fraud detection for credit card transactions, for example, or real-time machine learning and evaluation. And the choice of the data architecture actually defines what kind of range of the spectrum you can actually implement. And what I would like to do today is present you a data architecture with which we believe you can actually cover a quite wide spectrum. And this one is the following. So the modern streaming data architecture is built around stream storage and stream processing. Stream storage, as the name indicates, records the events produced by some sensors, mobile handhelds, some computers, or other sources, and stores them in your data center, for example. There, the streams are made available to the stream processing engine, and the stream processing engine can consume these streams and transform them into new streams. The stream processor could aggregate the data and generate a summary, which is stored in some long-term storage, for example, S3 for later usage or as a fallback. Or the stream processing engine can generate results, which are stored in some databases or key value stores, from where they are served to power your dashboard or generate your business report or even trigger other applications. So as you see, the important bits here are the storage part and the processing part. And what we do recommend this talk is to use Apache Flink and Apache Pulsar for that. So Apache Flink is well suited for processing all kinds of different streams, generating new streams out of it. It's capable of storing results and reading results from long-term storage, like files you stored in S3, for example. And it can even be used to build event-driven applications using Flink's stateful functions library. And so far, that's basically the processing part. For the storage part, we believe that Apache Pulsar is actually a very good fit. It excels at storing streams. It's a very good fit for long-term storage of data, and it can also be used to serve results to some downstream applications. Now, based on this modern data architecture, we would like to explain a bit more what Flink and Apache Pulsar is capable of doing. Let us start with Flink. So for those of you who don't know Apache Flink, at its core, it's a distributed runtime, which allows you to do stateful computations over data streams. It provides a set of APIs for doing that. So we do have like the data stream API and the process function API, which allows you to do stateful stream processing by giving you access to the basic building blocks of streams, state, and time. For those of you who are more interested in analytical workloads, Flink offers a SQL as well as the table API, which allow you to express your analytical logic on a nice high-level declarative way, without bothering too much about the details of state and time. And Flink also allows, as I've mentioned before, to build event-driven applications using the stateful functions library. In order to get an impression for Apache Flink, I've written down some numbers. So currently we have roughly 900 contributors, which is a number constantly growing. Apache Flink is one of the most active mailing lists in the Apache Software Foundation, and also has one of the most active repositories by source, visits, and commits. We have 16,000 GitHub stars, and the project consists of roughly 27,000 commits. The latest release is 1.13, and we have 170,000 downloads per month on Maven. With Apache Flink, you're able to build jobs which achieve sub-second latency. We have seen people using Flink to process more than 4 billion events per second, or in terms of size, more than 7 terabytes of data per second, which is consumed by the Flink job. For batch jobs, we have seen that people run batch jobs with more than 100 terabyte of input sizes, just to get an impression for what Flink is capable of. Flink is used by a variety of users for various use cases. So, for example, Alibaba uses it for machine learning and building recommendation models. Netflix uses it to build in real time session behavior profiles. UBS uses it for settling trades. Various ad techs use it for doing the accounting. And ING and Microsoft, for example, use it for machine learning to do like a real-time anomaly and fraud detection. So what are the ingredients or to the secret sauce of Flink, which makes it one of the most advanced stream processors out there? So independent of the actual stream processing engine you're using, almost all real-world use cases require you to do stateful computations. So Flink has first-class support for state, using the asynchronous barrier checkpointing algorithm to create globally consistent checkpoints in order to recover from failures, as well as to support resuming a job at a later point in time, for example. When dealing with real-time data, the data usually arrives out of order at your system. So in order to produce correct results, Flink has event time support, which exactly gets the unorderedness out of the stream. Leveraging the asynchronous barrier checkpointing together with transactional or idempotent sinks, Flink gives you end-to-end exactly once processing guarantees, so that you only see the results which are correct, so also under faults. Moreover, Flink is resource elastic, so that you can add resources, scale Flink jobs up and down, and remove resources. And last but not least, it offers a unified batch and streaming API, which allows you to do batch and stream processing on the same engine using the same APIs. So you don't have to rewrite your job dependent on whether you're processing historical or live data. And that is actually what I would like to drill in a bit more and explain to you how and why this is possible and why this is actually a good idea. So the underlying insight why this is possible is that actually everything is a stream. So stream is a sequence of data which is made available over time. So since all processes in our world take some time and don't happen instantaneously, actually all kind of computation can be seen as transforming an input stream into an output stream. So for example, if you have a CPU reading some data from memory and doing some calculations like let's say summing things up and producing the outputs. This can be seen as a stream processing task. Also, if you read data from a disk, you don't instantaneously read the whole file from it. You usually open a stream and read bytes or some other chunks of data over time. And the events of a stream can be of quite various forms. The decisive difference of when looking at streams is actually whether the stream ends at a certain point in time or whether it's infinite. So whether it's bounded or not. If a stream is bounded, then you can apply certain optimizations to speed up the calculation or the processing of the stream. And processing these kind of bounded streams is effectively the same as processing a batch of data. And if the stream is unbounded, then you have potentially to continue your calculation for an infinite amount of time and refining your results incrementally over time. The key insight here is that a batch or like batch processing is simply processing of bounded streams. And if you have a stream processor capable of processing unbounded streams, it's also capable of processing bounded streams. And that's why Flink can give you both stream as well as batch support. Let's take a look at a more concrete example. Let's assume that we have like in our database a table where we store for every room the temperature on a timely basis. And now we are interested in the average temperature in our rooms, in our house, in each hour. And yeah, that's the task. The way you can express and solve this problem is using Flink SQL API. And you could write the query the following way. You select from your sensors, which you group by where you group your sensor readings into 1 hour windows using the tumble keyword and specifying the length of 1 hour in the room. And then you select from this grouping the room, the end time of the window, and the average, and you calculate the average temperature. And once this is processed by Flink, which reads the input table, it produces an output table giving you the answer to your question. So how can this now be applied to a stream of let's say live sensor readings? In order to answer that, let's first take a look at the so-called stream table duality. The idea here is that actually that you can represent a table as a stream and a stream as a table. And the way it works is the following. Assume you have a table of data, and whenever you do a change, like a delete, update, or insert, you actually create a change event, which you emit to your stream, so that you have a stream of change events. By replaying then this stream of change events up to a certain point, you can actually materialize the state of the table at this point in time. And thereby you can basically go from a table to a stream and from a stream to a table. And that's property actually allows us to run the very same query on live data. Conceptually, what happens, you can think of it, Flink does it a bit smarter than how I explain it now, but conceptually you can think of it that you periodically run the query. For that to do, you first materialize your stream so that you create a table, and then you run the same query on the table, which gives you an output table. And by diffing the output table with the previous table, you can actually calculate the changes to the previous table, which defines the events which should be emitted to the change stream. And thereby, you can run the same query on live data as you've done on your historical data. And that is the beauty of things. All right, here I would hand it over to Addison, who tells you a bit more about Pulsar.
Thanks, thanks, Till. As Till mentioned, stream processing is really one of the most exciting ways in which we're evolving, being able to build some of these distributed applications and really to expand the usage of them. But in all cases, data has to come from somewhere, right? We have this very powerful compute engine in Flink, but we also need a storage system that can support getting the data in and out of Flink as is required. And as mentioned, while we have what's very common to have that streaming ingestion, having a system that also can support batch ingestion for some of these to truly be able to unify batch and stream processing is required. And that's what Pulsar aims to offer. And we're going to give a quick overview of the features of Pulsar that support this. But really the goal of Pulsar is to be able to evolve to meet the needs of a system like Flink that offers that low latency, high bandwidth streaming API, as well as the flexible architecture to support batch access. And so as a quick overview, I'm sure through the conference today, we'll dive a lot more in depth into how Pulsar works under the hood. But as a quick reference here, Pulsar like many streaming systems, acts as a distributed scale out log. So it allows for you to have topics or topic partitions, which can be spread across multiple brokers. And this can allow for high throughput parallel reads of topics across multiple machines and partitions. But additionally, each topic in Pulsar is also based on a segment-based architecture. So each of these individual topics also has a sequence of segments. And periodically, these segments close and become immutable. And because these segments are stored in the underlying mechanism of Bookkeeper, as well as being able to offload it into S3 through tiered storage, Pulsar's underlying storage architecture is really ideal for batch access as well. That allows you to have this historical data be stored and accessed in a batch mechanism while having the sort of the streaming layer that is really appropriate for stream processing on top. And so speaking about Flink and Pulsar together, we want to highlight exactly how these two systems can come together to be extremely powerful. And so this is really sort of the unified view of where we aim to have Pulsar and Flink be a strong pairing together. So once again, you have Pulsar, which is doing unified batch and stream Pulsar. So it can do all of the streaming mechanisms, and it also has this ability to offload onto tiered storage, which is commodity S3, other cloud storage systems. Whereas Flink brings unified batch and stream computing. So a Flink system capable of reading from batch data from tiered storage, as well as then able to transition to reading from a Pulsar and a streaming system, really provides a very powerful set of capabilities to cover that broad spectrum of use cases that Till mentioned earlier on in the presentation. But additionally, with a system like Pulsar, there's obviously the need to get data in and out of this system. And this is where Pulsar and Flink together, once again, have a strong set of combinations. So with things like Pulsar having Pulsar IO that provides syncs and sources in and out, obviously Pulsar has its support for its protocol as well as other protocols. And finally, Flink and Pulsar both having good capabilities to get that data out into downstream systems. And because of these strong capabilities, we're seeing both systems being adapted for this unified batch and stream storage and compute. And so organizations like Tencent, which is very well-known user of both Pulsar and Flink, is using these systems together for complex workloads. Likewise, Splunk, that is very much invested in the Pulsar ecosystem and with their new products around the DSP that is using Flink, and as well as other organizations like BIGO that is in live streaming and Micro Focus. There's a lot of organizations that are looking to adopt these and have adopted these applications for complex workloads. And so we want to talk a little bit about what's that connector at today. So today there's the Pulsar Flink connector, which supports Flink 112, 111, 112, and 113 support is dropping very soon. As mentioned, requires there's support on the connectors, and Pulsar supports exactly what source and syncs via the producer deduplication on the output side. There's full support for Flink schema with integration to Pulsar schema registry. So if you're already making use of Pulsar schema for codifying your data, you can easily use those schema in Flink to get full support for typed APIs, which also includes support for Flink SQL. And so with Flink SQL, there's support for batch and streaming modes. So you can run both these batch queries of bounded streams, as well as continuous queries using the Flink SQL support for Pulsar. There's also support for an upsert mode, which allows you to do some of this more fine-grained reasoning about ideas of inserts, updates, and deletes over a stream. And then finally, there's a really sort of exciting feature that Pulsar has support for key shared subscriptions, where these subscriptions allow for a higher source parallelism, the number of your topic partitions. So this can allow for some more flexible needs of being able to use a key shared subscription in Pulsar and not be tied to the number of topic partitions. And the link for that Pulsar Flink connector is shown here. And now I'm going to turn it back over to Till, who's going to do a demo of what these two systems look like together.
All right, thanks, Addison. Yeah, since so far all theory is great, we